I'm Prometheus, and this is Booksellets. Hello! I wish to talk about this book right here. Picked it up at the library sometime late last year in a library book sale. A first course in algebra by Mallory. This looked about 1960s-ish to me, so I thought, hey, maybe I'll see how algebra was done back in the days of slide rules. And I thought this might be fun. Break out the old pencil and paper instead of these calculators. A bit of good scratch paper time is good for the soul. You know what I'm saying? Has a wonderful, it needs to be cleaned a little bit, has the preface, copyrighted first in 1936, second edition, has all the stuff that you would normally expect in algebra. I'm like, okay, I see this. Practice exercises. Without pencil, give the values. Well, I was not expecting that. Now, to be fair, these problems aren't particularly hard once you know about algebra, but I do think it's interesting that on page 5 we're already getting rid of the pencil and paper. And in this book, in the later chapters, I want to share two things that I found interesting, and one of them drove me nearly insane trying to modify. And for that one, we shall start first. Hopefully it was a way of subtracting squares from each other. Now, I don't know if it's something simple like, say, 4 squared minus 3 squared. Nice, simple equation. We know 4 is 16. We know 3 is 9. We minus them is 7. Great. We figured it out. No problems whatsoever. Now, let's say we had to do something harder, like 25 squared minus 17 squared. Do you know what 25 squared is? Because I don't. I would just put it in my calculator. That's 336. Great. Move on. And think nothing else of it. But this book had a different method behind doing that. And that's what I wish to share with you today. It took 25 and added 17. It also took 25 and minused 17. And I was like, okay, this is kind of funky. What's going on here? So we run these additions. I'm just going to do it for the sake of brevity in the calculator. It's 42. And 25 minus 17 is 8. So now we have 42 and 8. Well, what do we do with these? The book said to times it. And if we punch that into the calculator, 42 times 8, we get 336. Let's take our original example of 4 squared plus 3 squared. And this one is really simple because we know that 4 minus 3 is 1 and 4 plus 3 is 7. 7 times 1 is 7, which jives with our previous answer. And these work fairly well. You can even do decimal numbers, such as, if we shall block off this area here so we don't get our numbers confused. Let's say we take 19 squared and minus 4.7 squared, then we can take 19 plus 4.7, 23.7, and we take 19 minus 4.7, and times that by 14.3, and we take these two numbers, and we get 338.91. And if we take the original squared numbers and punch them into the calculator, minus 4.7 squared, we get 338.91. So this was a really neat trick that I appreciated, considering it's a bit of removal of work. You still have to do a multiplication, but I think addition and subtraction is just slightly easier than trying to do 2 or 3 digit multiplication. I don't know when this would ever be useful in the age of the calculator, but I found it fun and kind of enjoyable to just run by. So then I thought to myself, can I use this same method, but can I add? So I started again with the simple 4 squared, and this time plus 3 squared. Alright, that seems fairly simple. We know that this equals 25 thanks to Pythagorean theorem, or just, 16 plus 9, 25. This is a number that books will use a lot thanks to Pythagoras. So this is a fairly comfortable number. We know it equals 25. So 4 plus 3, 7. And then maybe 4 plus 3 again, 7. No, that's 49. Oh dear. So needless to say, I spent about 2 nights of randomly scratching out on paper trying to figure out how to add squares using addition in some way, shape, or form. I didn't quite succeed, but I did go back in time a little bit, as I decided I would use an actual square to represent the void area, because the void area is what was throwing off the calculation. So, to explain what I'm talking about here, we have 4 squared, and we have another square of 3 by 3. Okay, great. So what are we talking about with void space? Well, I'm talking about this little area right here of 3 by 1 block. We have to take a 4 by 7 block and minus the 3 by 1 block, and that will equal 25. And that is what throws off my equations. We can do this similarly again with the other equation that we did up here. We have a big 19 by 19 block, and we wish to add a block of 4.7 by 4.7. Well, this is kind of a tricky little pickle here. Oh yeah, if you're not sure where I got the 7 here, I added 4 plus 3. These numbers get added just in case, because I did kind of gloss over that. So 19 plus 4 plus 7 we know is a 23.7, yep, 23.7. So the block total, if we were to include this void space and just form a rectangle, would be a 19 by 23 block, and we must subtract from it a 14.3 by 4.7 block, which should be this void area here. And just so I am sure, 19 plus 4.7 squared is 383.09. So this is the number we're trying to get. So we take our clear that so we have more. 19 times 23.7. And then we have our 14.3 times 4.7. Take 450.3 minus the 76.21 that we got, and we get 383.91. So it's this void space right here that throws off your equations, and that drove me absolutely up the wall for 2 nights in a row. Thank you, ancient mathematicians, for giving us square tables and log tables and sine tables and all this other stuff. And thank you, Mr. Texas Instrument, for developing things like the 555 timer and whatever other magic gizmos that go into this voodoo box that puts out whatever number I need or close to it. So that's what I did. The second trick that I wish to share from you is the multiplication of binomials. Now, in school, I always kind of hated these because, for the example, we have 3x minus 2 times 5x plus 3. And of course, if this is how I was taught in school, 3x, 5x, 15x squared, 3x times 3, plus 9x, negative 2 times 5x minus 10x, and then negative 2 plus negative 3, negative 6. And then we combine these two terms together, or combine all like terms. That would be a minus x minus 6. And so we have our answer right here. It gets the job done. I'm going to check to see how well this paper and pencil stuff is turning out. A little late in the video to be checking this kind of stuff, but... Oh man, you can't even see that. I am so sorry. Okay, I apologize for all that. There. Now you can see all of my horrible handwriting. Okay. I do apologize. Ugh. At least, hopefully, you can understand me, unlike other YouTube videos. So, that got the job done. Not extravagant. I always got terms confused and tried to combine stuff that didn't belong. In the book, First Course in Algebra by Malloy, new edition, very nice, it showed an alternative method that I personally prefer, though I've had some issues trying to multiply different numbers, such as trinomials and polynomials. And that was to set it up like this. And I found that really fascinating, because it sets it up in a similar style to traditional multiplication. It starts on the left side, 5 times 3, 15x squared, and 5 times 2, negative 10x. Then we have multiplied all those, so we jump over here. 3 times 3x, positive 9x. 3 times negative 2 is negative 6. And then we subtract down. Negative 6, positive 9, that's just an x for the negative, and 15x squared. So 15x squared, negative x, negative 6. Same answer we got there. And this works great for binomials, such as the example that was in the book, which was 2n minus 5m, and n minus 8m. Yeah, that's the numbers right there. So create the complex polynomial doodah that comes out of this. 2n squared minus 5nm negative 8m times 2n, negative 16nm, and negative 8m times negative 5m minus, plus 40m squared. And so we now just drop down all the things as we normally do in multiplication. 40 plus, and then we run these two negatives together, and 16 minus 5, negative 16 minus 5 is 21. I think that's how it goes, 21. It's a negative, and then the 2n squared. Haven't figured out trinomials yet, or polynomials, or if they just do the normal algebraic formula as I was taught. But I just thought that this was a fascinating look in the past of how certain mathematical things were done. And this one, I think, was how algebraic equations used to be written down as physical representations. Gosh, I don't even want to know how long ago. And yeah, needless to say, I got this book at the library. I found it a fascinating piece of Americana. And how do you know that you're looking at a 1940s book? Is because they include a picture of the USS Battleship North Carolina right on the front page. God bless America. I love this country sometimes. Includes all sorts of wonderful pictures randomly sparse throughout, such as this steel mill unit. This steel mill unit produces an exceedingly smooth, high-finish steel. Such mathematics is used in the design and construction of such complex machines. Don't talk to me about buying groceries here. Talk to me about steel mills and battleships. I don't care about my groceries. Give me the numbers for how to operate this stuff, or tell me how to mix chemicals together. This is what I love about this book. And yeah, that pretty much sums up what I wanted to say. Thank you for enjoying a little bit of Scratchpad time. Yeah, that's all I have. Have a nice day. Bye.